This video is going to walk you through how to graph rational functions. You'll see in comparison to the previous video that these functions have a little bit more variety to them, so we're going to talk about some of the other details you might run into. It's kind of the same process. You're still going to find vertical and horizontal asymptotes. You're going to graph things. You're going to find the domain range, but you're going to see, like I said, there's a little bit more variety to these type of problems. So let's go ahead and talk about this first function. We have y equals 6 over x squared plus 1. So the first thing we're going to do is we're going to find the asymptotes. So I'm going to go ahead and find the vertical asymptote and the horizontal asymptote. So vertical asymptote throughout this entire process is not going to change. In order to find a vertical asymptote, you're going to set the denominator, set it equal to 0, and solve. So let's do that. X squared plus 1 equals 0. Okay? Easiest way to get x by itself, we're going to go ahead and subtract 1. Square root both sides. Now, as you've learned many times over, square rooting a negative number means we're going to have an I involved and a plus minus. So if I square root negative 1, that comes out to plus or minus 1i. Here's what that really means, though. In order to have a vertical asymptote, you need to have a real number. This is an instance where this graph will actually have no vertical asymptotes. Okay? Because the result that we got from x was imaginary. If you have an imaginary answer, you can't show that on the graphs that we do. Now, there are graphs that exist that compare real and imaginary numbers, and you could work through this process. That's not what you're learning, though, right now. If you take much higher level math, you can learn about that. But for our purposes, if you have an imaginary number, you don't have a vertical asymptote that works on a real graph. So that means we're not going to have any dotted lines on the x-axis breaking stuff apart. That can happen. Most of the time it won't, but it can. The other type of asymptote is the horizontal, so going across the graph. Now, you learned in the last lesson that when you had an integer that was being added or subtracted to the fraction, you just pulled that horizontal asymptote and you're done. Most fractions aren't set up like that. What ends up happening is there are certain rules that you have to follow in order to figure out what the horizontal asymptote is. It basically boils down to three things. Let's take a look at this particular problem. What happens with these problems is you want to look at the degree of the numerator and the degree of the denominator and compare them. The degree of the numerator in this case is 0 because there is no variable, therefore there is no degree. The degree of the denominator is 2 because that's your highest exponent. If your degrees are different, if the larger degree is in the denominator, every single time, and you can refer to your notes on this, if the degree in the denominator is larger, the horizontal asymptote is always going to be y equals 0. So, y equals 0 means we're basically going to put a dotted line through 0. Okay, it's going to be on top of the x-axis, but keep in mind a y line is horizontal. So I know that's a little bit weird, but that's just how it works. That's where your asymptote is going to be. So your graph is going to approach 0. And again, the reason being is because the degree of the denominator is larger than the degree of the numerator. That's a rule that's going to hold true every single time. So we have nothing breaking it vertically. We only have the break horizontally on the graph. So now we're going to go ahead and plot points. So what's a little different about this is when you go through your table of values, you're not going to find anything where x has an error because you don't have a vertical asymptote. So basically, you're just trying to find enough points where you can clearly get a good sketch of the graph. So I'm going to pull a handful of points here. I'm going to go from -3 to +3. That should be enough here for this particular graph. So again, you do need several points to make sure you accurately sketch this. So we're going to go ahead and jot those down. And again, you get that right from your graphing calculator. So I'm going to go ahead and plot all of these points. So again, you want to be as accurate as you can be. So this graph's going to look a little different compared to most of the ones that we do. But again, this is still a rational function, so all good. And there we have it. So basically it looks like a big arrow pointing up, and then it shoots back down. But this is what our graph is going to look like. So there's your sketch. Okay. It's a little bit different looking, but mainly because there's no vertical asymptote. Graphs that don't have vertical asymptotes are going to look a little weird compared to most of the other ones that you're going to do. Now, you have your asymptotes put in, you have the graph plotted. Now let's go ahead and identify our domain and our range. So our domain again deals with our x's, our range our y's. So with our domain, I want to know how far left I can go to how far right I can go. Well, here's the nice thing about the graph here. There's an arrow pointing left, so that means I basically, quote-unquote, start at negative infinity. That's how far left it goes. Now I want to see how far right I can go. In this case, since there's no vertical asymptote, there's nothing blocking my path going infinitely right. I know it does, the graph does swoop up and then swoop down, if you will, once you hit the middle of the graph here, but it still infinitely goes from left to right without stopping. So our domain in this case is simply negative infinity to positive infinity. It goes left to right, no breaks. That's it. Our range is pretty similar to this, except we are going to have some more defined values with this. So if you look at your graph here, we want to see what's the lowest this graph is going to go. So you'll notice there's nothing in the lower half of my graph here because I have that asymptote at y equals 0. So the values of my graph basically start above 0. But if you look carefully at the graph, it doesn't go up infinitely. It goes up as far as 6. Now the way that we're going to note this, so you notice we've used just kind of parentheses here as a general thing. We use parentheses in this interval notation because it's what the graph can't hit. So basically it allows us to have a starting point, but it doesn't quite include that point. It's almost like inequalities in that sense. If it does include that point, so this graph actually does hit the number 6, okay, on the y-axis. The fact that it hits it, we are going to denote it with a bracket because that says, hey, 6 is included. If you look how we have a parenthesis with the 0, that 0, while it kind of acts as a starting point, it doesn't quite hit 0. It's approaching it, but it doesn't quite hit it. Same with the infinities. You can't define infinity. It's a value that has no definition to it. So we use parentheses there because they're just infinite. You can't hit infinity. So that's a little bit of the difference between that. You'll see that in a couple of these examples moving forward here throughout the year, where we will flip back and forth between the parentheses and brackets. But basically, parentheses are for values that can't be hit while on the graph, while a bracket is used for a value that absolutely is hit and used on your graph. So that's the first of the 3 examples there. Let's take a look here at the second one. So same idea. We're going to go ahead and work through this problem the same way. We're going to identify the asymptotes first, then we'll plot the graph, and then we'll figure out all the domain and range stuff. So let's take a look here first at our asymptotes. Vertical asymptote again, take the denominator, set it equal to 0. So we have x squared minus 9 equals 0. I'll add 9 to each side, and then square root. This one comes out a lot nicer. So again, I square root 9 plus or minus 3. So what that means is the fact that we did a square root in this problem, we have 2 answers. You have 3 and negative 3. What that means is you have 2 vertical asymptotes. That can also happen in these problems, especially when you start having squareds in your bottom here and you have to take square roots of things, you have to factor things, whatever the case may be. We can actually go ahead and put in 2 vertical asymptotes in this problem. So I'm going to go ahead at x equals 3. Asymptote at x equals 3 and x equals negative 3. So we're going to have 2 barriers as we go along the x-axis here. Something different to keep in mind, but again, it's all going to work the same way. Now, let's talk about the horizontal asymptote. This is going to be the second of our rules. So, once again, we're going to look at the degree of the numerator and the degree of the denominator. The degree of the numerator is 2. The degree of the denominator is 2. In this case, they are both the same degree. So to find the horizontal asymptote when you have the same degree in both the numerator and denominator, you take the leading coefficient of each of the expressions. So in the numerator, we have a leading coefficient of 2. In the denominator, we have a leading coefficient of 1. You take them, you divide them. What that means is we are going to have a horizontal asymptote at y equals 2. So again, to recap that, if the degrees are the same, both top and bottom of your fractions, take the leading coefficients of each expression, divide them, that's going to be your horizontal asymptote. So it's going to be y equals 2. I'm going to go ahead and put in that line. All right, so we have our asymptotes. Now we're going to go ahead and plot our graph. Now, you'll notice if you have multiple vertical asymptotes, that means when you look at your table, you're going to have multiple places where there's an error. So that also means when you take a look at the graph as well, there are more pieces than we've typically seen. So we've got a couple of branches on the left and right corners, and we have what almost looks like a parabola in the lower middle portion of the graph. So we need to account for all these things. So make sure with your table of values, you pull lots and lots of points. So I'm going to go ahead and basically start at -6. And I'm going to go all the way to +6, just to make sure I have enough points to account for everything that I'm going to need. Okay, so I'm going to go ahead and, again, I'm pulling these right from my graphing calculator. You do the same thing. So we're going to write everything out. We have a couple of errors. Again, your asymptotes are going to spit out errors, so -3 and +3 should show up as errors in your calculator. And again, here comes +3. So we got ourselves another error. And now we have everything that we need. So, long list, but it'll work for our purposes here. So, if anything, this is the easy part because you know how to pull these from the graph and you know how to plot. So, we're going to go ahead and plot our points. So again, try to eyeball the best that you can for the most accurate sketch. So here we have the first part of our graph. Now we get to our second part of our graph here. And the last part. All right. Funky looking graph, but it works. So now we're going to take a look at here. What's the domain? What's the range? So let's talk about the domain. The domain, again, we're looking left to right. So if I look, again, look, we got three pieces. Look at the graph in its totality. Leftmost, we got an arrow pointing left, which means we are going to go as left as -infinity. Now, again, I want to go right until I hit a break. So if I look at the first part of my graph here, the branch that's in the top left, as I approach -3, that's where I'm going to hit that break. So that's where I'm going to cap it off. Now, if I hop over that asymptote, all of a sudden the graph starts going again. If I look at the lower middle part, so I'm going to go from -3, I keep going right, and as I approach +3, I hit another break. If I hop over that +3 line, if I look at the top right, all of a sudden my graph is going again from +3 to +infinity. So in this case here, we had three pieces, so we're going to have, in this case, three domain sets, if you will, that are going to be connected. So it is possible to have more than one thing being connected to in the domains, if you will. So again, it just depends on how your graph is structured. You have to account for every break in the graph with that little U, that union connector. So in this case, it broke multiple times, so we have an extra piece here that's connected to the end. But that is your domain. We go from -infinity, hit -3, so it stops, then it starts again, stops at 3 as I keep going right, starts again at 3, and goes to infinity. Again, using parentheses for all of these values because in each of these cases, they are not included on the X scale. They're just values that they are approaching. Let's talk about range. So again, lowest to highest. This graph points downward, therefore it's going to approach -infinity. Now, I need to go up my scale. Now, typically, we would just look at the asymptote and say, okay, the asymptote, we go up to +2, that's where it breaks. But you really have to look at this graph carefully because there actually is a break before you hit the asymptote. Look at the piece that's in the lower middle. If I start going up, that only goes as high as 0. Okay, it doesn't go all the way up trying to approach that positive 2 line. It only goes up to 0. And it includes 0, so I'm going to use a bracket. All of a sudden, it stops. And then we have to make a break for it. So I'm going to go ahead. There's a break between. All of a sudden, I have to hop over the asymptote line of 2. So I'm going to basically start at 2, if you will, just past it. And then my graph points upward to positive infinity. So my range in this case, you'll notice the numbers in the middle are different for once. That can happen. It's not going to happen a lot, but it can happen with these graphs. So our range, again, the lowest it goes is to negative infinity. It approaches all the way up to 0 and just stops. It includes 0, so that's why I'm using a bracket and not a parenthesis. Then I have a little bit of a gap. I hop over the asymptote of y equals 2, and all of a sudden my graph starts again and climbs all the way to positive infinity. So that would be the range for my graph. Negative infinity to 0 included, and then start again from 2 to positive infinity. So the last example, we have same idea. Here's another function. So we have 0.75x squared divided by x minus 2. So, same deal. Let's go ahead and find our vertical asymptote. Now, this will be a little bit easier because we have a much nicer denominator. X minus 2 equals 0, x equals 2. That's a lot easier. So, x equals 2. Here's my asymptote. Now, this is the last of our horizontal rules. There's 3 rules. We've gone through the first 2 in the first 2 examples. Here's the last rule. Look at the degrees once again. The degree in the numerator is 2. The degree in the denominator, is 1. So this is a case where the larger degree is in the numerator. If the degree in the numerator is the larger one, this case, there is no horizontal asymptote. There is a horizontal asymptote that's referred to as a slant or oblique asymptote. You're not going to learn about that in this course. You take higher level math, you'll learn about it. But there is no horizontal asymptote if the degree is larger in the numerator. So we just write none for that. There is no dotted line going horizontally across the graph. And that's it. So a little bit less to work with here. A couple less breaks in that case. So let's go ahead and plot the graph. So since we know positive 2 is where we're going to have an error, because that's where our vertical asymptote is. Again, we'll pull a few points above, a few points below. And then we'll go ahead, as always, and just copy the table down. So, we're going to go ahead and do that. Now, when you plot this in your calculator, you punch it in, take a look at the graph. It's going to look a little weird because it kind of looks tilted, okay? And that's because of what is called a slant asymptote that you're not going to necessarily learn about in this course. So, you'll notice that both parts of the graphs kind of like swoop down and up, or up and down, or whatever you want to refer to it as. So you want to make sure you have enough points that you can see how it bends in both directions. It doesn't really bend in one way, it bends in two. So you do want to make sure you have enough points. That's why I'm pulling 5 numbers off of each side and not 4. Alright, so I have my points. All good. Let's go ahead and plot some stuff. So here I have the first part of my graph. And now here's the second part of my graph. Alright, so there's a big gap you'll notice in the middle of this here, especially with not having a horizontal asymptote. You'll see larger graphs because, again, with it being a slant asymptote, there's basically a different perspective of the way the graph lays out. So, again, plot your graph, you get what you get. Again, it should match whatever picture you see on your calculator screen. So, let's go identify domain and range. So, domain, I see an arrow that's pointing left, therefore, negative infinity is going to approach. going to approach that. Now I'm going to go right, 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 right. Only place where I see a break going right is that asymptote at 2. There's no random gap in between. And then I can start up again at 2 and go to positive infinity, because I see an arrow in the other part of the graph here that's pointing to the right. Now let's talk about range. Range always seems to be the tricky one. Don't know why, that just seems to be the case in these. So first off, we see definitely the graph's pointing downward. So the fact that it's pointing down means we're going to negative infinity to start. Now, how high does this graph actually go? So, starting from negative infinity and working my way up. The highest before we hit a clear break or gap in all the points in the graph. So if I look at the lower branch here, we definitely see it hitting 0 on the Y scale, but it doesn't go higher than that without it being a big break in space on the graph. So it hits 0, it's included, therefore a bracket. But we know there's more, so I'm going to make a connector. Now I see big gap in space, big gap in space. The next Y value that seems to be included is 6. So if you look at the upper branch here, we definitely have a point at 6 on the Y scale. And since that 6, again, is an actual physical point there, we're going to go ahead and put the bracket around it. And then the easier part, hey, it points upward, therefore goes to positive infinity. So that would be the range of that particular graph. So, a lot of details with this particular lesson here. Just to kind of recap it again. Vertical asymptotes are found the same way as you learned previously. Take the denominator, set it equal to 0. Horizontal asymptotes have different rules, all based on the degree of the numerator and denominator. You need to look at those rules in your notes. Those are things you're just going to have to memorize. Your calculator, again, will kind of give you a clue as to whether or not you have horizontal asymptotes that you can kind of imagine and put in on the screen. But knowing those rules will help you immensely to make sure that your graphs are right. Domains and ranges, again, domain you're looking left to right, range you're going from the lowest to the highest. You really do have to pay attention, though, to see where you might have gaps in your graph that aren't just at the asymptotes. So do want to pay attention to that. So that is how you graph rational functions.